So the our next topic for the discussion is discharge over a broad crested weir. So weir which is shown on the right side is a broad crested weir. So the very first question is that how can we define the whether the given weir is broad crested or not. So on the right side you can see so the length of this weir is L. So this is the length of the weir, and your h is the height of water above the crust. So you can see this is h is shown over there, capital H. Now this is just before the when it's reaching to the weir, that head we have to consider. So whenever your 2 times of L is greater than H, this kind of weirs are called as a broad crested weir. However, whenever 2L is less than H, such are called as narrow crested weir. Now, what another thing is that a small h which is just above the weir, you can see that head. This h is the head of the water at the middle of weir, which is assumed to be constant. That we have to take care for the evaluation of the discharge, or you can say the maximum discharge over the weir. In order to derive that particular expression, we are considering that at the middle of this particular weir, the head is a small h, which is shown on this one, and this will be considered to be throughout same, and this water is flowing at a constant speed of v. So this small h is your head of water at middle of the weir, head of water at the middle of weir. Another thing that v is the velocity of water over the weir. So we are going to evolve for the evaluation of the expression for the discharge over the weir. So in order to derive the expression, it has been assumed that both this particular things are constant. So assuming this particular phenomenon, we will evolve the expression for the discharge over the weir. So there is another important thing, that evaluation of the velocity of the water over the flow. So what will be the v? That is very important thing. So in order to estimate the value of this particular v, we will go for the use of the Bernoulli's equation of the still water surface on the steep side and the running water at the end of the weir. So if you can see, we have to take the two consideration points for the applying the Bernoulli's theorem, and then we will figure out what will the velocity of the v. So the point which are considering in this equations are, first point we will consider is this one. You can see this particular point and this particular point. So let's say this point is 1 and this point is 2. So we will apply the Bernoulli's theorem at the location of 1 and at the location of 2. So let's start applying the Bernoulli's equation at location 1 and location 2. So this location 1 is your condition of still water. This is your still water. What we are assuming that this water is still, and the location and the velocity at this location, whatever the velocity, if you are assuming that velocity is v, that particular velocity is 0. However, the velocity at the section 2 is small v. Okay, this is your upstream side of the running water at the end of the weir. Okay, so using the Bernoulli's theorem, at location 1 and location 2. So let's first of all write the expression of the Bernoulli's theorem, then we will go for the evaluation. So the Bernoulli expression can be written as P over rho into G plus V square divided by 2G plus Z. That should be constant. Let's figure out the this particular expression at location 1 and 2. So if we will figure out that location at location 1, so P is 0 because this is your atmospheric pressure. So we are, if in the terms of the gauge pressure we are solving our equation, we can write that this particular expression is going to be 0 at location 1. And similarly, we are assuming that this particular thing is still water. So at the location of still water, your velocity will be 0, then the v square divided by 2g will again be 0. Then if we are considering that this is our datum, this is our datum, and with respect to this datum we are measuring all the heights of the water, then at this particular location what we can say that this head is capital H. Now at location 2, if we do this same thing, so similarly P over rho g at location 2 will again be 0 because the top surface is exposed to the environment, and here the atmospheric pressure exists, so gauge pressure is 0, and we are writing our equation in the terms of gauge pressure. So plus then v square, so velocity at this particular location is v divided by 2g plus at this particular location, so z, your level of the water surface above the datum is small h. Now if we solve this particular equation, we will get this expression that v square divided by 2g comes out to be h minus h. So we can write this equation that v is equal to under root 2g h minus h. Now there is an important thing that if you will notice that throughout the derivation of the previous expression for the discharge of the weirs and notches in the case of rectangular and triangular, we have used this expression that v is equal to under root 2gh. However, this particular equation is somewhat different from this particular equation. That you have to take care. If you are considering this point clearly, then the derivation for the or the evaluation of the expression of the discharge over the Weir will very be easy. For the expression of discharge, we can write at that Q is equal to your coefficient of discharge, yeah, that is your CD, multiplied by the area of flow into velocity. So we can write that this is CD, your area is L, L is the length of the weir, and height of the water is H, so L into H is your area, and multiplied by the velocity. So velocity is under root 2g h minus h. So you can see that your CD is different, CD multiplied by area into velocity. Now if we just rewrite this equation, this will look like that CD into L under root 2g h, and we are taking small h inside, so h square minus h cube. So this is the our expression for the Q over a broad crested weir. This is your expression for discharge over a weir. Now there is a very interesting thing that in the expression of the discharge over the years we have discussed so far, that Q was completely related with the H. So either in the power of h 3 by 2 or h 5 by 2, especially in rectangular and triangular notches. However, in the expression of this broad crested weir, our expression is dependent on the h as well as small h. That's important. So now it becomes that how will we maximize the discharge over the broad crested weir. So in order to maximize this q, that is a very simple mathematical problem. So in order to maximize this q, what we can just differentiate this q value with the small h, and then we will go for the that dq over dh, that should be 0 at that location. Either we'll be having the maximum discharge or minimum discharge. So just looking at the problems, we can figure out that what value of the small h will give us the maximum discharge. So let's start this particular problem. Before proceeding that, we can quickly see that this CD is constant, L is constant. So only that particular thing that is going to be control the value of Q, that is your under root 2G, that is also constant, capital H. One mistake is over there, you can just clear it. So h over h square minus h cube. So that particular thing will decide whether the q will be maximum or not. So what we can say, that whenever the value of h over multiplied by h square minus h cube, whenever this particular value will be maximum, then we will be having the q maximum. So instead of taking the whole expression, we can just figure out the maximum discharge by using this particular aspect, that d over dh is h into h square minus h cube. That particular thing, whenever going to be 0, then we will be having the value of small h, that will give the expression of that will give the maximum value, this particular expression that is under the consideration. So what we have to do is that in order to maximize the q, we have to use the value of a small h, so that this particular expression should be maximum. So if we differentiate, this will look like 2h into h minus 3h square is going to be 0. Then we can write it 2h is equal to 3h. That means h should be 2 by 3 times of h. So once we get this value of h, now just in order to get the q maximum, we will just replace the value of this small h with the 2 by 3 times of the h. So let's solve this particular thing. So the q maximum, that will be CD multiplied by L multiplied by 2G h square minus h cube. This was our original expression. Here we will replace this small h value, this particular small h value, with this one. So if we'll put this value, this expression will look like q max is equal to CD into L. So we are taking under root 2G outside, so that we need not to take care of this thing. And if inside, if we replace the small h with the 2 by 3 times of capital H, this will look like h multiplied by 4 by 9 h square minus so this is h cube, so this will be 8 by 27 h cube. So if we simplify this equation will look like CD multiplied by L under root 2 G 4 by 27 H cube under root. So if we just put the values of so Q max is look like this one. So just replacing the value of G with the 9.81, we will get the Q max value will be 1.7047 into CD multiplied by L H raised to the power 3 by 2. Earlier what expression we were using, when this was a narrow, we were using this expression was a 2 by 3 CDL H raised to the power 3 by 2. So what difference only we can see that the coefficients which are over there, this is 2 by 3, that is equal to 0.667. However, in the case of broadcasted, this expression is 1.7047. You can see this is come at least 3 times higher than this value. So using a broadcasted weir, we can maximize our discharge over a weir. A broad-crested weir of 60-meter length has a 60-centimeter height of water over its crest. Find the maximum discharge. Take CT values equal to 0.6. So first is the neglect velocity of approach. I mean, first part is without the inclusion of the velocity of approach. So A should be there, that is missing over there. So this is the A part, and B part is if the velocity of approach is to be taken into the consideration, find the maximum discharge when the channel has a cross-sectional area of 60 square meter on the upstream side. So let's go for the solution. So first of all, we'll note down all the values which is given to us. So the length of the weir, that is L, is 60 meter and has a height of head is your H is 60 centimeter, that is 0.6 meter. So next is the CD value is given as 0.6. So neglecting the velocity of approach, if we figure out the Q value, then we can write that Q is equal to for broadcasted weir is 1.705 multiplied by CD multiplied by L multiplied by H raised to the power 3 by 2. So if we put all the values, 1.705, 0.6, L is 60 meter multiplied by 0.6 raised to the power 3 by 2. So answer will be 28.52 meter cube per second. So that's the first part. Let's go for the second part. So this was part A. Now we will go for the part B, that is B. So where the velocity of approach will be considered. Now so for this thing, we have to use the formula again. This is the corresponding to the Q max. So same formula is there, only the VA is involved. So when the velocity of approach is there, so Q max for the broadcasted weir, the formula can be written as 1.705 multiplied by CD multiplied by L, and in brackets this is H plus HA raised to the power 3 by 2 minus HA raised to the power 3 by 2. Now, first of all, we have to figure out the value of HA, and HA will be find out by the VA. So in order to get the VA, this VA can be Q by A. So Q is given to us, that is the from the previous Q value. So this Q value is 28.52. Now divided by the area. Area of this is your channel is 60 square meters, so that is 60. So this will give us a VA value of 0.475 meter per second. Corresponding to this, HA value will be VA square divided by 2G. So it's a square. So HA is coming out to be 0.0115 meter. Now we will put these values of HA and all, then we'll get the Q max. So Q max is equal to 1.705 multiplied by 0.6. L is your 60, and then H is given to us that H is 0.6. So this is the 0.6 plus 0.0115 raised to the power 3 by 2 minus 0.0115 raised to the power 3 by 2. That will give us the value of Q max. So Q max will be equal to coming out to be 30.5 meter cube per second. So that is the Q max when the VA is considered. So you can see the difference between these two things. So when VA is approached, the value of Q max is 30.5. However, without the consideration of VA, this value was 28.52. Now we will take a problem on the submerged weir. So the problem says that the height of the water on the upstream and downstream side of a submerged weir of 3 meter length are 20 centimeter and 10 centimeter respectively, and coefficient of discharge for the free and drawn portions are 0.6 and 0.8 respectively. So we need to find out the discharge over the weir. So let's go for the solution of this problem. So here we need to take care of that CD value for the free as well as the drawn portion are different. So that's why we will use this discharge equation into the two section. So for such kind of problem, first of all we'll figure out what the values are given to us. So the height of water on the upstream side is given to us, H is equal to 20 centimeter. So this H is equal to 0.2 meter, and height of the water on the downstream side. So this is the upstream side, and similarly height of the water on the downstream side can be written as small h, that is 10 centimeter. So this is 0.1 meter. And now the length of the weir is given to us, that L is equal to 3 meter, and we have to take the CD1 and CD2 because two coefficient of discharge are over there. So that is 0.6 and 0.8. Now if we will write down the formula for the discharge, so discharge over the drowned weir will be in the counted into the two portions. So this is the summation of the discharge through the free portion and discharge through the drawn portions. So the discharge over the free portion plus discharge over the drawn portion. So for both these segments, we have to write down the equation. So let's say this is the total discharge is Q. So Q can be written as 2 by 3. So first portion we are saying that CD1 and multiplied by L multiplied by under root 2G and H minus H raised to the power 3 by 2 plus 2 by 3 CD2, and then L multiplied by H multiplied by 2G H minus H. If we now replace all the values, so this will be 2 by 3, CD1 is 0.6, L is your 3, and then under root 2 multiplied by 9.81 and multiplied by this is 0.2 minus 0.1 and raised to the power 3 by 2 plus. I just made a mistake. This value will not be the 2 by 3. So CD2 will be the is given the 0.8 and then L is 3 meter and then again H. So small h is 0.1 and multiplied by the 2 multiplied by 9.81 and then capital H is 0.2 minus small h is 0.1. So if we solve this problem, the total discharge is coming out to be 0.504 cubic meter per second. So this is the our answer for using the droned weir. So this is the first portion. If you can see, this is the first portion and this is the free portion, and second portion discharge is for the droned weir portion that we have to calculate this separately. And if the CD1 and CD2 are the same, we have to use, if only one discharge value is given to us, then we will use the uniform CD. Otherwise we have to also take care that the coefficient of discharge are different, then we will use the different value. So this is our answer, and that's how all the problem related with this chapter is concluded over here.